Hello everybody, today we're going to be talking about Chapter 10, Biological Rhythms and Sleep. And so animals generate endogenous 24-hour cycles of wakefulness and sleep. We call a 24-hour cycle a circadian rhythm, meaning that about every 24 hours you at some point get tired at night, fall asleep, wake up, stay awake during the day, and fall asleep again the next night. And that pattern happens again and again over about a 24-hour period. There are other circadian rhythms. Temperature is another rhythm that kind of goes on a cycle, a 24-hour cycle, where you can see that as you're falling asleep, temperature decreases and then slowly starts to increase. And then again increases during the day and then starts to decrease as you fall asleep again at night. And this circadian rhythm of temperature again happens endogenously in our bodies. So biological rhythms are regular fluctuations that happen in any living process. The circadian rhythms, as we talked about, cycle about once every 24 hours. But there are ultradian rhythms that repeat more than once a day. So rhythms that go through the entire cycle more than once a day, something like your blood circulating through your body. Or infradian rhythms, these repeat less frequently than once a day. Again, they're on a cycle, but less than once every 24 hours. This might be something like the menstrual cycle. So the suprachiasmatic nucleus, or SCN, is part of the hypothalamus and seems to be the main control center of our circadian rhythms of sleep and temperature. It's located above the optic chiasm, and damage to the SCN results in less consistent body rhythms that are no longer synchronized to the environmental patterns of light and dark. And in fact, if you even isolate these cells from the SCN, they will continue to show a circadian rhythm for days or even weeks. And they've done transplant studies that prove that the SCN produces circadian rhythms. These hamsters with SCN lesions, and those hamsters showed no circadian rhythms. The endogenous 24-hour rhythms were no longer there. And then these hamsters received a tissue transplant of SCN tissue from hamsters who had a very short circadian rhythm. So instead of being 24 hours, about 20 hours. And the circadian rhythms in those hamsters were restored, but their circadian rhythms matched the shorter 20-hour cycle from the donor. So these cells from the suprachiasmatic nucleus seem to be extremely important for providing the circadian rhythm. Oh, sorry, here we go. So the suprachiasmatic nucleus regulates the pineal gland, which is an endocrine gland located posterior to the thalamus. The pineal gland secretes a hormone called melatonin that increases sleepiness. And melatonin in our body is typically secreted about 2 to 3 hours before bedtime. So if you typically go to bed around 10 o'clock, body starts to produce melatonin or secrete melatonin around 7 or 8 o'clock at night, and that's a signal in your body that you're getting ready for bed and we're getting ready for sleep. Melatonin is actually sold as a sleep aid. You might have heard of melatonin. And by taking it about 2 to 3 hours before you want to go to bed, that can change your internal clock. And often people will try melatonin when they are jet lagged, if they're traveling to another part of the country or another part of the world, and they sort of need to reset their internal clock. They might try melatonin when they get to the new time zone, take it about 2 to 3 hours before they're ready to go to bed, and that would mimic the typical way our body releases melatonin when it's time to get ready for sleep. So, how do we study sleep? This is a good question because the thing we're trying to study is really hard to study. Sleep, the person is asleep, right? So you can't ask them questions of how they're doing or what they're feeling because they're asleep. We do study sleep in what we call a sleep laboratory. These are basically bedrooms that are all adjacent to an observation room, and the experimenter spends the night awake, observing the participants as they're sleeping in the bedrooms. I don't know if I want to use the word pleasure of doing some sleep research. It's pretty hard, particularly if you like to sleep, because you have to stay up all night while other people your participants are sleeping. And so how do we study sleep? Well, again, we can't ask people really what's going on while they're sleeping. So instead we take electrophysiological measurements where we attach electrodes to the person, and we attach electrodes in different places. We attach them to their scalp. Those are called EEG, electroencephalograms. So we attach electrodes to the scalp, and they're basically just glued to the scalp, and that will measure brain waves. We attach electrodes to the outsides of the eyes, and not the eyeball, but the skin around the eyes. And these are called EOG, or electrooculogram. That will monitor eye movements. And then we take EMG, or electromyogram. We attach these electrodes to the chin to monitor muscle activity. So we get measurements of brain waves, of eye movements, and of muscle activity. And the EEG records an average of all the electrical potentials in the cells in the different parts of the brain. So remember, how does your brain function? That's all the way in the beginning of the class, the action potential, which is an electrical signal. And so the EEG records this electrical signal. And so here's somebody who is in a sleep lab. Boy, that looks comfortable, doesn't it? And we've got the EEG electrodes are on his scalp. We've got the EOG, the EMG, and all of those wires basically from those electrodes that are just glued on, get bundled up together and put into this computer, and it takes all the measurements as the person is sleeping. So what do we know about sleep? And although we know some, more of sleep is a mystery to us than probably what we understand. So when the person is awake, these are the EEG, the brain waves, we see what's called alpha and beta activity. And this is the pattern of an awake, alert person. It has different frequencies, and you need to be an EEG expert to really be able to read these brain waves. But you've got beta waves in here. Those are more irregular, lower amplitude. That means less tall, shorter waves. And then occur when a person is alert, and again, that's called beta waves or beta activity or desynchronized EEG. This is just a very awake person. And then alpha waves, those are regular, more medium frequency waves, and those are prevalent when the eyes are closed, the person is relaxed, but they're still awake. Okay. Now, as the person falls asleep, they go into what we call stage 1 sleep. That's when sleep has just begun, and there's a transition there between wakefulness and sleep. This is the sleep where, and maybe you've been around someone who's done this, they've fallen asleep, you might have even heard them snore for a second, and you wake them up, and they go, what, I wasn't sleeping. Yes, you were, I heard you snoring. This is that stage 1 sleep. It's a transition. The EEG is very irregular, has these very jagged, irregular brain waves, and the brain activity is starting to decline. It's starting to slow down. You can see that as opposed to these very, very jagged, very quick brain waves when someone's awake. We're starting to kind of slow our brain waves down. What happens here? The heart rate is slowing down too. The muscles are starting to relax. The eyes kind of close and roll about, and this lasts for several minutes, this stage 1 sleep. After stage 1, the person goes into what we call stage 2 sleep. This is about 10 minutes later. Here are the brain waves, and the brain waves are characterized by what we call sleep spindles and K complexes. The sleep spindle, and again, you would really need to be an expert to read these waves. I would never ask you to look at a brainwave and tell me what stage someone was in. But you've got these bursts that happen, these sleep spindles in stage 2 that last for about half a second. And there are these bursts of activity, and possibly this might be, again, nobody quite knows. One of the theories is this is a mechanism that starts to decrease the brain's sensitivity to sensory input, because that's something we're trying to do as we're going into sleep, is you're sort of shutting off your awareness, your reactivity to things going on around you. If every noise you heard, every word you heard, every sound from outside your window woke you up, that would be a problem. And so maybe these sleep spindles are starting to decrease our sensitivity to the sensory input around us. You also see these K complexes. These are sudden, sharp waveforms that occur spontaneously during stage 2 sleep, but can often be triggered by an unexpected noise. So again, maybe when there's a loud noise outside, something, and the brain is trying to sleep, but it's still registering that sound. You're in that transition of not quite deep sleep yet. Your brain registers the sound, and you get this K complex. But these two are the sleep spindles and K complexes are specific to stage 2. When we get to stage 3, now we're in what we call slow wave or deep sleep. And you can see the EEG actually looks very different here. You have these very slow, tall waves, we call them delta waves, at about 1 per second, and the brain is very deeply asleep when you see these waves. And at this point, you're in, again, we call slow wave or deep sleep. Your heart rate is quite slowed, your breathing is slowed and steady, and the brain activity is very slow, and we call this a very highly synchronized neuronal activity. Everything is just very slow and calm. This would be what we would call our deepest sleep when we get to stage 3. And so in a typical night, we go through sleep cycles. For a young adult, sleep time ranges from 7 to 8 hours. About half the sleep is stage 2. About 20% is REM sleep, and I'm going to talk about REM sleep in 1 second. That's this purple part. And the cycles last for about 90 minutes. And you go through, starting at awake, stage 1, stage 2, stage 3, stage 2, and up to REM, and then down back to stage 2, stage 3, stage 2, and up to REM. You've got some brief awakenings every now and then, again back down to stage 1, stage 2, stage 3, stage 2, and up to REM. And you can see you cycle through these stages, and each cycle takes about 90 minutes. Over the course of the night, your slow wave sleep, you have more slow wave or deep sleep, that stage 3 sleep, in the beginning of the night, much less at the end of the night, almost going away. And in opposite to that, we have less REM sleep in the beginning of the night and more REM sleep in the later sleep cycles. So what is REM sleep? And you might have heard that term before. Well, about 90 minutes after the beginning of sleep, there's this big change in all the physiological measures that we take in a sleep lab. And we name this type of sleep REM, or rapid eye movement sleep. So what happens when someone enters REM? Well, their EEG, the brain waves, become very irregular and fast, similar to stage 1. I'm going to bring this back. Here's REM sleep. And up here is stage 1, and you can see they look very similar. So the brain gets very active again instead of that very slow, calm, deep sleep. It's very, very active again. The eyes are darting back and forth, and again we've got those EOG, those electrodes around the outsides of the eyes, and we can see the eyes are moving back and forth. Again, you might have seen this if you've ever been around someone who's sleeping, and all of a sudden while their eyes are closed, you can see the eyes moving back and forth. Well, that is REM sleep. And the EMG, the muscle activity is silent. There is a loss of muscle tone during this time. This is also known as paradoxical sleep, REM sleep, because it's a very deep sleep in some ways, because look, you're practically paralyzed at this point because there's this loss of muscle tone, but it's a very light sleep in other ways. The EEG, the brain is moving back and forth, the eyes are moving back and forth, so it's in some ways very deep, in some ways seems very active. In REM sleep, a person is very easily aroused and woken up by meaningful stimuli. So if someone says your name when you're in REM sleep, it's easy to wake up, and you appear alert and attentive when you're awakened. If you wake someone up during REM sleep, they'll almost certainly report they've been dreaming. REM sleep is when we think dreams occur. If you wake someone up during that slow wave sleep, they'll report that they weren't dreaming. We have very vivid dreams. Those vivid dreams seem to occur in REM, and they're characterized by lots of visual imagery, sounds, smells, emotions. You kind of believe that you're there. It's a very realistic experience. A nightmare, as I'm sure you all know, is a very long, frightening dream that awakes the sleeper from REM. This is different than something called night terrors. Night terrors are something that you can see. My daughter experienced this for a while. It's a pretty notable experience where people, or in my daughter's case, child, wakes up from stage 3 sleep, so very, very deep sleep, and they're extremely afraid, they're crying, their heart is beating, they can't catch their breath, but it's not because they're having a nightmare where they can tell you some kind of story that has happened in the nightmare that's very scary. It's just more of this autonomic, this body terror that happens. And very often when children have experienced night terrors, even though their eyes are open, they're not quite awake. They're still almost in this sense of deep sleep, but they're just experiencing this very scary experience there, that you can see that they're very fearful, but they're almost not even awake or aware of what's happening. That's very different than a nightmare that you can wake up and say, wow, that was scary. This is what happened in my nightmare. So what is the function of REM sleep? And again, this goes where we'll be saying we don't quite know. We do know REM sleep is important because REM sleep deprivation is not good for people or for animals. And they can actually do REM sleep deprivation where the person or animal is still able to sleep and able to sleep the right amount of time, but researchers will prevent the person from getting REM sleep. And so as the person is all hooked up to all of the electrodes, you can watch, and the person's awake, and then they're in stage 1 sleep, stage 2, stage 3, back up to stage 2, and right before they hit REM, they wake you up. Oh, good morning. Hello. It's your friendly researcher here. All right, go ahead and go back to sleep. They go back to sleep and they go, stage 1, stage 2, stage 3, back to stage 2, and wake them up before REM. And so in that way, the person can get 8 hours of sleep, but never REM sleep. And so we can get REM sleep deprivation. And we can see that as that happens, the pressure to enter REM sleep builds up. that when you finally do allow them to sleep again, they go much more quickly into REM sleep. It's like the body is wanting to get into REM sleep. And that subjects report feeling irritable, anxious, have problems with concentrating, weight gain, temporary personality changes, just from REM sleep deprivation. So not total sleep deprivation, just not having REM. And we found this in people deprived of 4 to 7 nights of REM sleep. An animal experiment with REM sleep deprivation led to death. So again, we know REM sleep is important. And as I said, there's a rebound that once you're REM sleep deprived, then REM sleep starts to increase when someone's allowed to go back into REM sleep and have a normal night's sleep, increased to a much larger proportion of the night's sleep when their sleep was undisturbed. So we know REM is important, and if you don't have REM sleep, it can lead to devastating consequences. And in REM sleep, we dream. Why do we dream? Again, there are theories more so than answers. Possibly important for organization of brain or learning. So that's one of our thoughts, is that, and you might know this, that if something important happens during the day, you tend to dream about it. And that may be your brain's way of sort of integrating that information, organizing the information from the day, and kind of helping you learn whatever that information was from the day. There's another hypothesis called the activation synthesis theory, and this is that the brain produces random electrical energy during REM sleep that stimulates different memories and visual experiences that are stored in your brain, and the brain needs to make sense of these random electrical impulses, and so it weaves together a storyline, and that creates your dream. And that might make sense when you think of your dreams, and that they're often very hard to follow and they don't make a lot of sense. And you'll explain a dream to someone and say, well, this doesn't make sense. I was at my house and then I don't know, I started flying and then I saw a giraffe. And they're very often and don't seem to make a whole lot of sense. And maybe that's just because you have these different little electrical impulses kind of going off as you're sleeping, and your brain is trying to make sense of it and sort of weaves it together as a dream. Sleep patterns across the lifespan. What do we know? Well, infants sleep a lot more than adults. Infants will sleep up to 16 hours during the day and night, and at different parts. They wake up, eat, and then go back to sleep. And infant sleep has more REM sleep, right? They have shorter sleep cycles and more REM sleep, which seems to be essential in helping to develop the nervous system. And then as we get older, overall sleep time goes down, and the amount of REM sleep decreases as well. Brain areas that underlie wakefulness and sleep. So in order to have a sleep cycle, we need to have parts of our brain that keep us awake and parts of our brain that help us sleep. So areas important for wakefulness, one area is called the reticular formation. This is in the central core of the brainstem, receives axons from sensory pathways that activate the reticular formation, and activate this electrical activity activates the brain. So it helps keep us awake, this reticular formations. And if you have lesions to the reticular formation, that can lead to persistent sleep, not being able to wake up. The locus coeruleus, this is another brain area located in the dorsal pons that is activated in arousal, attention, and in response to meaningful events. Seems to be very important in memory. Interestingly, the locus coeruleus is inactive during REM sleep, so the idea of memory and remembering your dreams is kind of hard. Let's see, the basal forebrain, this is located near the hypothalamus, and in the basal forebrain there are both waking and sleep-related cells which send axons to your thalamus and the cortex. The sleep-related cells seem to be important for slow wave sleep, and destruction of this area leads to total insomnia in rats. So it definitely helps us sleep. And when you don't have that brain area, rats cannot sleep. The sleep-related cells release GABA. GABA is an inhibitory neurotransmitter, and so that helps you, again, calm your body down and get ready for sleep. And lesions to these cells produce prolonged periods of wakefulness, as do drugs. If you take a drug that inhibits GABA, again, people are more likely to be awake. What about REM sleep? Well, the pons has a REM sleep center. During REM sleep, it sends GABA to inhibit spinal neurons, so we don't act out our dreams. That's kind of interesting. We said that during REM sleep, you sort of lose muscle tone, and it seems that there's this sleep center in the pons that sends GABA, or an inhibitory transmitter, to your spinal neurons. That's important because you don't want to act out your dreams. Often you have dreams that you're doing all sorts of things, and if you could act them out, get up, walk around, that could be very dangerous. And so this part of the brain seems to be important to stop that from happening. REM sleep also induces what we call PGO waves, pons geniculate occipital, PGO. And so these are bursts of electrical activity that originate in the pons and then to the LGN of the thalamus and then to area V1 in the occipital lobe. And that's interesting because we've got pons, thalamus, V1, and dreaming REM sleep is a very visual phenomenon. So it kind of makes sense that your occipital lobe is activated during REM sleep. Even though you're not seeing anything, your eyes are closed, but your occipital lobe is active. We also see increased activity. I've said pons, thalamus, and the amygdala. We'll talk about the amygdala. That's important in emotions, and dreams can be very emotional. And so arousal of the amygdala may have some relation to the emotional aspect of dreams. We also see prefrontal cortex suppression. And prefrontal cortex, we will talk about this as well, is important for planning and keeping things organized. So if the prefrontal cortex is suppressed, that may relate to this disjointed kind of illogical nature of dreams. Here's those PGO waves, pons, geniculate, occipital, that we see this burst of kind of waves of energy during REM sleep. Talking about some abnormalities of sleep. So most common is insomnia. Insomnia can be brought about by many causes. If you're worried, stressed, you're living in a place where it's excessively noisy, serious illness, pain, allergies, almost anything can cause a brief amount of insomnia. And then the longer it goes on, the more significant it is. We have three classifications of insomnia. There's onset insomnia, which is trouble falling asleep. The person has a lot of trouble falling asleep, but once they're asleep, it's all right. They're good. There's termination insomnia. These are people who wake up way too early. So they have no trouble falling asleep. They stay asleep, but then they wake up at like 2 or 3 in the morning and can't go back to sleep. And then maintenance insomnia. This is someone who has no trouble falling asleep, but once they're asleep, they keep waking up. They awaken frequently during the night, and so that is a problem too. People fall asleep while their temperature is declining. We saw that in the very beginning of this lecture, and wake up when it's rising. And so sometimes if people have we call it a phase shift in their temperature, that may cause some type of insomnia. So if you see here, normal circadian rhythm of body temperature, that as the body temperature is declining, people are falling asleep, and as it is increasing, they're waking up. But if your body temperature is 3 hour, we've got a phase delay here. And so instead of falling asleep when the body temperature is falling, their body temperature hasn't fallen enough yet. And so they may have difficulty getting to sleep until their body temperature is in kind of that right area for falling asleep. Or a 3-hour phase advance, the body temperature starts to rise too early. That typically wakes you up, but it's waking them up too early. So body temperature and sleep are very closely related. There's also sleeping medication or drug dependency insomnia, and this happens when people have trouble sleeping and they take sleep medication to help them fall asleep. But then they develop a tolerance of the drug. They need more and more of the medication in order to sleep. And when they stop taking the drug, and when we talk about drugs and drug abuse, we'll talk about tolerance and withdrawal, you get an opposite effect. So when you stop taking the drug, if you're going through some kind of withdrawal effects, you experience the opposite effects of the drug. So if the drug typically made you sleepy, like a sleeping medicine, then you're more awake. So when you stop taking the medication, you're actually more awake. It's even harder to fall asleep. And then they may end up taking the medication again or more of the medication to fall asleep. And so it can be a cycle of what we call drug dependency insomnia. Another abnormality of sleep is called sleep apnea. Sleep apnea is the inability to sleep and breathe at the same time, and as you can imagine, that is a problem. Nearly all people who snore have occasional episodes of sleep apnea. For serious sleep apnea, people can go over 1 minute without breathing, and this can happen over and over, 10, 20, 50 times a night, where they are doing fine, and then all of a sudden they kind of hold their breath, stop breathing. Typically what happens is they wake up, and they don't even maybe know they're waking up, but their body kind of wakes up, they start breathing again and fall back asleep, and then maybe have another episode of this sleep apnea where they stop breathing, and then their body as a reflex basically wakes them up, they start breathing again, and then fall back asleep. And again, most people, when they're experiencing sleep apnea, don't even know it's happening because they're still, not really aware of themselves holding their breath or of these little awakenings during the night. What happens is they wake up very tired, they're exhausted, they don't know what's wrong with them. It's really either if they would go to a sleep lab, they realize something is wrong, they don't understand why they're so tired, they may diagnose sleep apnea. Or if someone sleeps in a bed with another person, often the other person will say, hey, you just stopped breathing. We need to go get this fixed. It's another possible cause of sudden infant death syndrome. Heard about sudden infant death syndrome where it doesn't appear to be any other cause, but infants will die, and it may be due to sleep apnea in infants. Other causes of sleep apnea are obesity if you're lying on your back. Basically, your neck is more heavy. It can kind of put pressure on and make your airway even narrower. And in the elderly, we seem to see that the brain mechanisms and the brainstem for breathing may cease to function during sleep, and that's a significant problem, as you might imagine. How do we deal with apnea, sleep apnea? Oftentimes people wear a mask called a CPAP, where you put a mask on your face and turn it on, and it pushes highly pressurized air down your airway into your lungs, and so you're constantly keeping that airway open. All right. Another abnormality of sleep is narcolepsy. This is when you have sleep or aspects of sleep that happen at inappropriate times. So what are some of the symptoms? You can have a sleep attack. This is an overwhelming urge to sleep that lasts for 2 to 5 minutes. The person wakes up feeling refreshed, but all of a sudden they're just awake, having a normal day, and then all of a sudden will just fall asleep. Cataplexy, this is another symptom of narcolepsy. This is when a person will suddenly wilt and fall. It appears to be a phenomenon of REM sleep, that idea of muscular paralysis that happens during REM sleep, but that occurs at an inappropriate time. So all of a sudden they lose their muscle tone and they'll just fall. Seems to be precipitated by strong emotions or sudden physical effort. So as somebody is I don't know, laughing, really enjoying something, having a very strong emotion, and then you see this cataplexy of the loss of muscle tone. And then sleep paralysis. This is an inability to move just before the onset of sleep or upon waking up in the morning. Again, this idea of this aspect of REM sleep, the paralysis that we have during REM sleep, but kind of continuing as the person is awake, but they still have a little bit of muscle paralysis, or just before they fall asleep, kind of REM sleep intruding on on wakefulness. And this is actually something that people who don't have narcolepsy experience as well. You may have experienced it, or somebody my roommate in college used to have this, which she said was very scary, but didn't have the rest of the symptoms of narcolepsy. So of course, if there's something you're concerned about in your sleep, go to a sleep doctor, but you can have this sleep paralysis without all of the, without having narcolepsy. Another symptom of narcolepsy, hypnagogic hallucinations, and this is when you basically are awake and have these hallucinations, but we feel as though it's the mental component of REM, again, intruding into wakefulness. This shouldn't say REM sleep here, into wakefulness. So the idea of those visual things that you see during a dream, they're happening when you're awake. So narcolepsy seems to be produced by a brain abnormality that causes the neural mechanisms responsible for various aspects of REM to become active at inappropriate times, and it appears to be primarily a genetic disorder. Questions. Why do we sleep? Again, we don't have the answers, but some ideas. Conservation theory, we sleep to conserve energy, right? Our body temperature drops, we save energy, our metabolism decreases, and so sleeping is a good way to conserve energy, particularly at night when you can't, if you're not nocturnal, can't go out and hunt and gather. It's dark, we can't see very well, right? And so sleep is a good way to conserve energy during that time. The opposite would go for animals who are nocturnal, right? They see really well in the dark, and that's when they do their hunting. And so during the day, they would fall asleep to conserve energy. The restoration theory is the idea that we sleep to restore our body. And you've probably had that feeling where you're just like, I just need to sleep. My body just needs sleep. And the idea is that after being exerted all day, we need to restore our body and brain. And that's why we sleep. There is support for that. Research that after several days of not sleeping, a rat's immune system eventually fails. They lose resistance to infection and their brain activity ceases. It's like if they don't have that chance to restore, their body starts to break down. We also sleep more during the time we're sick. You probably have remembered that at some point when you're sick and all you want to do is sleep all day and sleep all night. That sort of makes sense because if you're in this restoration theory, if you're restoring your brain, restoring your body, well, when you're sick, you've kind of got to do more of that to heal. And so you do sleep more. But it is just a theory. We don't have all the support. We also have some evidence that doesn't support that theory, such that how long we sleep is not dependent on how much activity you do during the day. And again, you've probably had days where you do nothing, sit around all day, but then you're still able to sleep at night. If this was the total answer that we sleep to restore our bodies, then it should be correlated, that the more you do during the day, the more you sleep at night, and we don't always see that. Another possibility for why we sleep is to enhance learning and strengthen your memory. That your performance, and we have evidence for that, your performance on a newly learned task is often better the next day if you have adequate sleep during the night. That somehow what you've learned is consolidated and learned and kind of reinforced while you're sleeping. And we know sleep deprivation is not good. It's not healthy. Partial, which is some sleep deprivation, or total, leads to increased irritability, difficulty concentrating, being disoriented. And after someone has had sleep deprivation, when they're in recovery, they sleep more than usual after that period of deprivation. You see stage at night 1, stage 3 sleep shows the greatest increase relative to normal, and you have less of that stage 2. Your body wants that deep stage 3 sleep. And on nights 1 and 2, we also see REM sleep increasing relative to normal. And it also seems to be more intense. You have more rapid eye movements, etc. All right, everybody. Well, thank you so much. And I hope this helps you get a good night's sleep. All right, thanks. Bye.